Whenever you try to write your own programs, you're going to encounter the nemesis of all computer programmers: bugs. Just like some criminal in a detective novel, bugs can cause trouble when you least expect them, they can hide out for a long time, and they can be tough to track down and eliminate. Now, detectives eventually track down and capture criminals not only through systematic, persistent effort, but also increasingly with the help of some forensic tools. Likewise, in programming, systematic and persistent effort to find and eliminate bugs is greatly enhanced by the use of tools, which we'll meet in this lecture. Things like test suites and debuggers. Now, the term bug has a long history, going back to Thomas Edison. When Edison was working on an improvement to the telegraph, he ran across a design problem that he fixed by building what he called a bug trap. And he continued to use the term bug to talk about problems that he was encountering in his designs, and the term took on wider use. Now, one of the most famous examples in computer science came from Grace Hopper, working on one of the earliest computers, the Mark II, back in 1947. The Mark II was an electromechanical computer. There were actual physical relays that would move to make connections. And in one case, when the computer wasn't functioning correctly, the source of the problem was a real bug, a dead moth caught within the relay. The Mark II team started using the term bug to refer to problems that they encountered. And the term bug has been a common term in computer science ever since. Now let's be clear about exactly what a bug is. A bug is just a mistake made by a programmer. It's an error, fault, or defect. Sometimes there are different connotations among those different terms, but they're all basically the same thing. It could be that something was typed in wrong. It could be that the programmer didn't think about some interaction between two parts of a program, or got interrupted and forgot to come back to finish something. Or maybe it was just a bad design from the beginning. Now, even the best programmers have bugs, although it's true that the number of bugs you create will go down a little bit as you gain experience. But what makes some of these programmers great is that when they do have bugs, they can find and eliminate them quickly. Now, obviously, it's better to just not make mistakes in the first place, but it's even more important to be able to find and correct your mistakes after you inevitably do make them. The easiest bugs to find are usually syntax errors. Syntax errors happen when you've mistyped something in the program. See if you can spot the error here. While is missing the letter E. That's a syntax error. Here, the programmer forgot how a function's defined and didn't pass the parameters correctly. Now, most syntax errors are going to be relatively easy to find, because the interpreter or the compiler for any high-level language isn't going to let you go forward. Python's interpreter-style compiler will give you a syntax error message and stop the program from executing if it finds a problem like those. Now, these are the types of errors that you could find just from examining the syntax of the program before it's even run. Now, other errors that you might not find until the program is actually running are called runtime errors. Many runtime errors will involve someone giving input that's incompatible with what's required. Maybe you have code where you ask the user for a file to read in. And what happens if the user gives you a file that doesn't exist? Or maybe you're asking for a month, expecting the person to enter a number, and they actually type in January. Well, this would cause your conversion from a string to an integer to fail. A third category of error, and the ones most difficult to find, are logic errors. Here, the computer will run the statements just fine, but the output will be incorrect. Remember that computers are dumb, and they just do what they're told. They follow the instructions exactly, and they don't know that they didn't do what you wanted them to. There can be lots of different forms of logic errors. Some logic errors are like syntax or runtime errors, except that the interpreter lets them through. You might forget the way something was spelled or how you capitalized, but the computer does not catch the mistake. Instead, the new spelling can end up creating a new variable with a different name. The interpreter doesn't know what you meant to say, only what you actually did say. So you have to be careful. You'll have written code that's perfectly valid, it's just not doing what you wanted it to. And that can make it difficult when reading over the code to even notice the mistake that you've made. You might not remember the order of parameters in a function, and maybe reverse the month and day. You meant to say February 8th, and instead you said August 2nd. You might accidentally switch a greater than to a less than, or you write equals when you meant to write plus equals, or you put in a minus where you meant to have a plus, or you forgot to indent. Maybe you meant to hard code that your favorite color was yellow, but you accidentally wrote that it was blue. All these errors are logically valid statements, and the program runs perfectly fine with them. So an interpreter won't catch them for you, and they won't usually cause a program to crash. They just mean that you get a wrong answer. Now, even more problematic is when you have a logic error in your thinking, and you actually meant to have a line like that, but you shouldn't have. In other words, you really thought that you wanted that less than sign, or that equals assignment, or that subtraction, but it wasn't the right way to solve the problem. Now, these are some of the most difficult errors to track down, because eventually you have to realize that the problem is in your thinking, not in the code. Fortunately, there are ways of dealing with all these logic errors. Let's look at some code from a program that we've seen before, which reads in data from a file and stores it in a list for later analysis. But I've made one change to it that introduces an error. I wonder if you can see what it is. Take a look, but if you don't find it, that's totally fine. Now, what usually happens is we do not see the error right away. You have to discover it. Here's the general approach I recommend for debugging. There are basically 3 stages to follow. First, we need to thoroughly test our code. We've seen testing before, but now we're going to see how to do it in a much more thorough and precise manner. Testing can tell us that there is an error somewhere. Second, we need to isolate the error. We want to find the particular conditions that caused the bug or error to occur, and then hone in on that particular place where the error is occurring. And finally, once we've found the bug, we need to fix it, which might actually be a complex task on its own depending on the bug. Let's look at how this will work on the example we saw earlier. Remember that our first step in debugging is to thoroughly test. We'll run the program, enter a date like, April 6th, and get some result. We see the result and it looks reasonable at first glance. Well, maybe the high temperature averaging 92 seems a little high for April, but at least we've got something that's not totally unreasonable. Let's try a different day, like April 30th. Whoa, we've got a major error here, a runtime error, one that's causing our program to crash. There's clearly a bug of some sort, and it looks like it's a divide by zero problem. We'll need to move on to the second stage, actually isolating the bug. Now, we were lucky enough to stumble across a problem. That's what beginners often do, if they even test at all. Just sort of do a few random things and see what happens. This kind of ad hoc testing is much better than no testing at all. But it's not efficient. We can write our tests more systematically. We can build up what's sometimes called a test suite, a set of tests that will run against our code to make sure it's working right. The code should be tested on the test suite anytime there's an addition or a change to the code. Now, in an ideal setting, you'd even write the test suite before writing code. But realistically, programmers develop their tests along with their code, in most cases. As your code grows, you can grow your test suite also. Usually, the most important tests to run are the extreme cases, what are called edge cases or corner cases. Think of a checkerboard. The squares in the corners or on the edges are different from squares in the middle. They don't have the same number of neighbors, for instance. In our particular program, this means that we need to think about the extreme dates. The first and last day of the year are extreme, and it wouldn't hurt to check the first and last days of some other months. Then we should check a few cases in the middle, just to be safe. We want to make sure that we handle more than just the edge cases, but it's rarely helpful to test lots of these. A few of them is plenty. And finally, we need to check any special cases. For dates, there's an obvious special case. Okay, you can include Christmas in your birthday, but I'm talking about leap year. We need to check February 29th. So, our test set should have, at minimum, January 1st, December 31st, some day in the middle of the year, and February 29th. And to be on the safe side, we should check a few other dates also. Now, If we run on this set of test data, sure enough, we run across the same bug we found earlier. January 1st comes out okay, but testing December 31st gives us the crash that we found before. Our next step is to isolate the bug. We have to look for clues as to what's causing the problem, eliminate the things that we check that are working correctly, and gradually focus in onto the one problem. Now, one of the oldest methods for debugging, and one that's still used in many circumstances, is just to insert a lot of print statements into the code. So, in this case, we had a runtime error at the line where we computed AVG low, or average low. So, we'd insert a couple of print statements right before that to print out the values that went into the calculation. If we ran the program, we'd find that both values were coming out to 0. And that would give us some information, and we could use that as a clue as to what was going wrong, and insert more print statements to narrow in on the problem further. As in this example, inserting print statements is a useful approach to see what's happening along the way. It's especially useful if we want to print out one thing from a long loop. Plus, it's something that you can try in almost any programming language. To start honing in on a bug, after you've run the print statements, you can leave them in the program, but comment them out. You can do this by putting a hashtag in front of them or enclosing them in triple quotation marks. Commenting them out will keep them around in case you want to run them again later. However, a more systematic way to isolate bugs is to make use of a debugger. Now, despite its name, a debugger is not a magic wand that we wave to remove bugs automatically. It's not like running an antivirus software that does everything for you. I mean, that'd be cool. I wish we had that. But a debugger is still a tool that'll help us examine our code in detail so that we can isolate a bug. Now, there are several debuggers out there. Each of them works a little bit differently, but they all provide the same basic functionality. I'm going to show you how to use the debugger integrated into PyCharm. One of the great things about using an integrated development environment like PyCharm is that the debugger is right there waiting for you to use it. Like many programming tools, debuggers can include lots of features, and you could spend hours going over all of them. I'm going to focus here on a few of the important ones that'll be most helpful. You know that green arrow in the upper right corner that we've been clicking to run our programs? Right next to it, we see a little green bug. This starts the debugger. Now, when we click on that bug, the debugger will start, very much like running the program did. It'll first ask for the data file to use, and then we'll enter in the test case that we know makes it fail. December 31st. When the program crashes, notice that the line where the code crashed is highlighted. The line has a division, and we're getting a division by 0 error, so this makes sense. Now, we have the line of code where the program's crashing, but this is important. This line of code is not actually the problem. This line of code is just where the problem became apparent. Usually, when you have a bug in your program, the bug is actually in one place and it doesn't become apparent until much later. Now, down in the window, where we see the output, what's called the console window, we also see a tab labeled Debug. If we click on the Debug tab, we see 3 new sub-windows called Frames, Variables, and Watches. We click in the Variables window, where we see all of the variables that are active in the program, along with their value on the current line. For us, the current line is the place we crashed. Now, our division on the line where we crashed was trying to divide sum of min by num_good_dates. If we scroll through that variable list, both sum of min and num_good_dates are 0. So, we now have our first clue as to the problem. We seem to have a sum of 0 and have found no dates matching the date we entered. That's weird. We should have plenty of dates that match December 31st in the set. So, we have a first clue here. It seems we didn't find any good dates. Now, we need to determine why we didn't find any good dates. It's okay to make a hypothesis and check it. Let's suppose we don't have a good date because we didn't read in the month and day correctly. In that case, the day and month variables should be incorrect. If we scroll through the variable list, we can see that the day is set to 31 and month to 12, so that's not the problem after all. Maybe instead, the problem is that our data from the file is missing. We can look at that variable, which is called datalist. Well, in datalist, we see a bunch of information. So we certainly have something there. It's not missing data. These easy checks aren't finding anything. Since we have the clue about there not being any good dates, and the number of good dates should be the number of dates in the good data list, that probably means that the good data list is empty. So, sure enough, if we examine the list of variables in the debugger, we'll see that the good data list is empty. Let's examine that part of the code. Now, I want to show you another useful feature of debuggers, the breakpoint. A breakpoint is a way of telling the computer, run the code up to this point, but then stop or break. It's like we stop the program waiting on user input, though here the user isn't involved. We can set a breakpoint by clicking right before the line of code in the editor. Notice the red dot that appears? That indicates that there's a breakpoint at that line. Breakpoints are a great way to stop a program partway through and examine what values everything has. So, in this case, we'll set a breakpoint right after creating the good data array, right on the for loop. We know that sometimes creating good data works since it worked for January 1st, but sometimes it doesn't, since it didn't work for December 31st. Now, we should start the program again and enter our information, the file name, and 1231. Notice that now the program comes to a stop where we set the breakpoint. That line of code is highlighted in the screen, and we can look and examine variables. Scrolling through the list, we see that our variables all seem to have the values we'd expect, so it looks like everything up to this point is probably okay. But we know that after this loop, things aren't okay. We never get any entries in good data. So we want to see what happens as we go through the loop. Why are we not getting any dates put into the good data list? We can now look at another tool we have available to us in the debugger, and that's the step over command. If you look in the debugger window, you'll see a set of arrows. The step over arrow will basically take you to the next line of code. It executes whatever is on the current line and then stops on the next line. If we click that button, we can look at the variable list and see there's now a variable called single day, and it has data for the first day. Now, the if statement that we're on is going to compare the month and day to the first two elements of single day. In this case, those elements are both 1, that is, it's January 1st. So obviously there's not a match. If we click step over, we'll go back up to our for statement. Besides step over, we also have a step into button. Step into is used when there's a function call. Instead of just doing the whole line of code, your next step is into the function that's called. It's a great way of checking whether the function code is behaving like you expected. A good debugger will have additional ways to show you where you are in the program and what's going on. In PyCharm, the frames window shows the sequence of functions that have been called. If those functions are nested, like one frame inside another, it shows you how deep you are in the program. If a function calls a function that calls a function that calls a function, then this window would show you that whole sequence of function calls. The watches window lets you set up some variables to be watched. This is more systematic than just inserting a lot of print statements. You can add variables to the watch window, and their value will be updated there as you step through the code. It just saves you the time of scrolling through the variable list over and over. In this case, let's add single day, since that's the one that we're looking at. If you're tired of going line by line, you can always hit the play button, the green arrow in the debugger window, and it'll keep running until it hits another breakpoint. Okay, but for us, we're still trying to figure out this part of code, so we'll check how this loop is working some more. We click on step over, and sure enough, single day is updated. It now shows as being a list, 2, 1, 2000, etc. Let's see our if statement at this point. We're comparing the month to the first element and the day to the second element. Whoa, hold on, something seems a little wrong here. We went to our second day, and it was the first element in the list that changed. This is the element that we're comparing to month, so it looks like we went from January 1st to February 1st. Now, maybe the data really did go from January 1st to February 1st, but that doesn't seem likely. So we've got another clue. We don't have a definitive answer yet, but we're getting close. I can feel that we're closing in on that bug. Let's take a few more steps through to see how things progress. If I keep clicking on Step Over, we'll see that single day keeps updating on each iteration of the loop, and that it's the first element that keeps going up by 1. We can keep doing this until we see that the single day has a first element of 13. Now, we know there's no 13th month, so this must be a problem. And now we finally have some proof that we've got our bug trapped. Our code is comparing the first element to month and the second element to day. But the way the data is stored, the first element is the day and the second is the month. No wonder we were getting no matches for December 31st. We were trying to find a match for the 12th day of the 31st month. So, at this point, we've isolated our bug. The debugger was a key part of this. With our bug now isolated, we know exactly what the problem is. We now turn to fixing the bug. The thing you should not do is just change this one line of code to get rid of the bug and go on. Instead, you need to think about where this bug really originated. Was it in this line, where we compare day and month to the wrong elements? Or was it when we first built the list and decided to put day first and month second? Or maybe there are other places in our code where we assumed that month came before day. Before we make any change to the code, we need to think about how the change we make is possibly going to affect the other parts of the program. In this case, the issue is relatively isolated. We don't really use the data list for anything else, and there's not another check like this one. So, we could just modify this one line within the for loop. We just swap around day and month in the if statement, and that should fix the error. Or, we could change the way the data list is constructed to begin with. We could just build up data list with month first, then day. Either way, what's the next thing we should do? Celebrate that the bug is fixed? Of course not. We first need to determine if we actually fixed the bug. The way we do that is by rerunning all of our tests. We want to make sure that our fix didn't break something that was already working, and that it fixed the problem that it was supposed to. So, in this case, we'll run the code for our little test suite. January 1st, and December 31st, and February 29th, and some other day in the middle. And now it seems to work, telling us that we really did seem to fix the error. So, our process here was to come up with a complete set of test cases, run these tests, and then for any error we found, isolate it and fix it, and then test that fix. Not all errors will show up as crashes. In fact, most errors will simply be erroneous values produced. The process for dealing with them is the same. Now that we've got a way of dealing with logic errors and syntax errors, let's turn to runtime errors. These are the things that come up when a program is running, typically due to unexpected input of some sort. Now, notice that although the example we just ran through was something we saw at runtime, we're not calling it a runtime error. The end effect is not that different, but what we had was not just a failure to deal with an unexpected case. We actually had a wrong concept in our code, where we assumed data was entered one way when it was actually entered another. We thought the data was being stored as month then day, instead of day then month, and that's why we call it a logic error. However, the main difference between logic errors and runtime errors, and maybe the only reason to care about the difference, is the way we treat these errors. Python, like many other languages, has a special way that it can deal with runtime errors. This is through exceptions. Exceptions are a way of handling the special error conditions that can occur when a program is running. For example, trying to open a file that doesn't exist or convert a string to an integer when the string turns out to be a word instead of a number, or trying to divide by 0 will usually cause a program to crash, printing out an error. Exceptions are a way of taking these problems and handling them in some way so that the program doesn't just have to crash. For instance, if opening a file to read it in fails, we can ask the user for a new file name. Exceptions are handled in Python through what are called try-except blocks. A try-except block is basically a way of containing code that might create the exception. You start with the statement try, followed by a colon. Then, indented is all the code for which you possibly want to check for an exception. Following that is an except statement, identifying which error you want to deal with. And finally, indented again is the code to run in case you do run into that error. Let's see a particular example. In this case, we try to open a file that a user entered. If there's an error in opening that file, we have an except statement that catches the exception. In this case, it prints a message and opens some different file. Now, we had to know that OS error was the name of the exception we were looking for, and that means we needed to know the possible errors. Here's a list of built-in exceptions for Python, arranged in a hierarchy. There are a large number of different exceptions defined, and a mechanism for letting users define new ones. To see a list of the standard exceptions, like here, look up a Python language reference. But to give you an idea, I've listed a few useful ones here: type error, OS error, and zero division error. Now, a segment of code could potentially raise more than one type of exception. We can deal with this by using multiple except blocks. For example, if we're writing a function that takes in a couple of numbers and divides one by the other, we could run into issues in a couple of places. We could have a problem if someone passes in a string or something weird. This would create a type error. Or we could end up with a zero division error. Or maybe there's some other error. We can list each category of error in its own block. And for the other errors, we can have a single except block that's used to catch all of them. If needed, we can have two other types of blocks. The first of these is an else block. The else block comes after the except statements and specifies code to run if there were not any exceptions. Only if there were no exceptions raised in the code in the try block does this get executed. There can also be a finally block, which comes at the very end after any except or else blocks. The finally block will get executed after everything else, whether there were exceptions or not. Now, most of the time, exceptions get raised when a regular system error occurs. But as a programmer, we can raise an exception ourselves. What this means is that we basically raise a flag saying, hey, such and such out of the ordinary thing happened here. The command you use to do that is called raise. For example, if you have a date function and want to ensure that the month lies between 1 and 12, you could check for this and raise a type error exception if the month is of an incorrect type. Or, say you had a function that was designed to look for a pattern of length 5 within a sequence. If you received a pattern of a different length, it would make sense to raise an exception. Now, let me give a word of advice. Be careful when using exceptions. They can be powerful ways to handle some of the runtime errors that would otherwise cause your program to crash. But they can easily be abused to do things that are better done with other code. Exceptions should be for exceptional situations. For example, if you're checking whether the month is between 1 and 12, it's often just as easy to check for those cases with an if-then statement and ask the user to re-enter data. And this use of standard code is much more normal looking than an exception. So, avoid using exceptions for cases that can and should be handled at the point the problem's detected. Conversely, use exceptions only when the problem really can't be handled at the point of detection. For example, exceptions are about the only way you can deal with the pattern matching example where the wrong length pattern is given. And if an exception does happen, you want to handle it. That's what the try-except blocks are for. Let me tell you about a really expensive case where an exception was not caught, and the impact of that. One of the most expensive software bugs ever was due to an exception in the inertial guidance system of the European Space Agency's Ariane 5 rocket. To quote the official report from 1996, the exception was caused during execution of a data conversion from 64-bit floating point to 16-bit signed integer value. What happened basically was, their software tried to convert a float to an int, but it wasn't able to, because the float was too large. The number stored in the 64-bit floating point was too large to fit in the 16-bit integer. So, the software, which was written in the language Ada, generated an operand error exception, which just means there was an error in something being operated on. However, they didn't have anything to catch the exception and handle it. As a result, the guidance system just failed completely. The rocket and its payload of 4 satellites were all lost, at a cost of $500 million. When we debug, we're looking for 3 types of errors. Syntax errors are usually found by the compiler, and logic errors can be eliminated with the help of our debugger tool and steady systematic testing and examination. Runtime errors generate exceptions, and these are things we can catch and deal with in our program, using the try-except blocks. The more time you spend working through a debugger or writing all of your test cases, the better you'll become at debugging, and thus at coding. Use of test suites and systematic debugging also make it much easier for other programmers to be interested in trying out any code you might write, or inviting you to contribute toward other projects. Now, speaking of program sharing, in the next lecture, we're going to learn about importing modules and packages that can dramatically improve what we're able to do in our own programs. I'll look forward to seeing you then.